Next time you're in a window seat, watch the wing during takeoff. It bends upward, visibly, sometimes by several feet at the tip, and the metal skin flexes like something alive. Every passenger notices it. Almost nobody finds it alarming anymore. But here's what most people don't realize, that flex is not a tolerated weakness in the structure. It is the structure. The wing is designed to bend, and if it couldn't, it would snap clean off. So why do airplane wings actually look the way they do? Swept back, tapered, slightly twisted, and curved upward at the tips? The common explanation starts with lift. Air moves faster over the curved upper surface of the wing, creating lower pressure above and higher pressure below, and that pressure difference pushes the wing up. That explanation is not wrong. But it is dangerously incomplete. Lift is easy. Any flat plate angled into a wind generates lift. A barn door generates lift. The real engineering challenge was never producing lift. It was producing lift without killing everyone on board. The first thing to understand is that a wing is not just a lifting surface. It is a fuel tank, a structural beam, a vibration damper, and an aerodynamic compromise all built into a single shape. The swept-back angle most passengers associate with speed actually exists primarily to delay the onset of shock waves as the aircraft approaches the speed of sound. A straight wing on a Boeing 737, cruising at around Mach 0.78, would begin forming localized supersonic airflow over its upper surface, producing drag that rises so violently engineers call it the drag divergence boundary. Sweeping the wing back 25 degrees effectively makes the wing see a slower airflow component perpendicular to its leading edge. Not a faster wing, but a wing that tricks the air into behaving as though the plane were slower. But that raises another question. If sweep helps at high speed, why not sweep the wings even further? Because sweep carries a penalty. A highly swept wing produces less lift at low speed, which means higher takeoff and landing speeds, longer runways, and more dangerous approaches. The 35-degree sweep on a 777 is not an optimum, it is a negotiation between cruise efficiency and the reality that every flight must also slow down. Then there's the taper. Wings are wider at the root and narrower at the tip. Most people assume this saves material. The real reason is aerodynamic. A tapered wing distributes lift more efficiently along its span, approaching what engineers call an elliptical lift distribution, the shape that produces the least induced drag for a given amount of lift. The Spitfire's famous elliptical wing platform achieved this almost perfectly, but elliptical wings are expensive and difficult to manufacture. A simple straight taper gets roughly 95% of the benefit at a fraction of the production cost. Not elegance, but economics. And those curved-up wingtips, winglets, are solving yet another problem. At the tip of every wing, high-pressure air beneath curls upward and around to the low-pressure region above, creating powerful vortices that trail behind the aircraft. These wingtip vortices represent wasted energy, and they are strong enough to flip a small aircraft that flies through them. A winglet acts as a vertical barrier, weakening that curl. Modern blended winglets on a 737 reduce fuel burn by roughly 4 to 5%. That translates to hundreds of thousands of dollars saved per aircraft per year. But if winglets help, why not make them enormous? Why not a 10-foot winglet on every plane? Because the answer is not just aerodynamics, it is gate space. Airport terminals are built to fixed widths. The wingspan of an Airbus A380 already pushes the 80-meter box limit at most international gates. Every inch of winglet added to the span is an inch that must be accommodated on the ground. The folding wingtips on the Boeing 777X, hinged panels that fold upward after landing, exist not because of any aerodynamic need during flight, but because the wing is too efficient to fit at a standard gate. Not a flight problem, but an infrastructure compromise. Even the subtle twist built into most wings, called washout, where the tip is angled a few degrees lower than the root, exists to ensure that during a stall, the root section loses lift first while the ailerons near the tip remain effective. The wing is designed to fail partially and predictably rather than all at once. To me, that is what makes a wing worth looking at more carefully. It is not a single answer to a single question. It is an accumulation of competing constraints: speed versus safety, efficiency versus manufacturing cost, aerodynamics versus airport infrastructure, each one resolved not by genius invention but by disciplined compromise. Not intuition, but decades of hard trade-offs frozen into aluminum and composite. Have you ever wondered why the engines are mounted beneath the wings rather than above them, even though that would keep them further from the ground?